Bipolar transistor is a switch. When used as an AC signal amplifier, the transistor's base biasing voltage is applied in such a way that it always operates within its active region, that is, the linear part of the output characteristics curves are used. If the circuit uses the bipolar transistor as a switch, then the biasing of the transistor, either NPN or PNP, is arranged to operate the transistor at both sides of the IV characteristics curves. The areas of operation for a transistor switch are known as the saturation region and the cutoff region. This means then that we can ignore the operating Q point biasing and voltage divider circuitry required for amplification, and use the transistor as a switch by driving it back and forth between its fully off, that is cutoff, and fully on, mean saturation regions as shown. 1. Cutoff region. Here the operating conditions of the transistor are zero input base current, zero output collector current, and maximum collector voltage, which results in a large depletion layer, and no current flowing through the device. Therefore the transistor is switched fully off. The input and base are grounded. Base emitter voltage VBA is less than 0.7 volt. Base emitter junction is reverse biased. Base collector junction is reverse biased. Transistor is fully off, that is cutoff region. No collector current flows. Vout is equal to VCA is equal to VCC equals 1. Transistor operates as an open switch. 2. Saturation region. Here the transistor will be biased so that the maximum amount of base current is applied, resulting in maximum collector current, resulting in the minimum collector emitter voltage drop, which results in the depletion layer being as small as possible, and maximum current flowing through the transistor. Therefore the transistor is switched fully on. The input and base are connected to VCC. Base emitter voltage VBE is greater than 0.7 volt. Base emitter junction is forward biased. Base collector junction is forward biased. Transistor is fully on, that is saturation region. Maximum collector current flows. VCE equals 0, means ideal saturation. Vout equals VCE equals 0. Transistor operates as a closed switch. Then the transistor operates as a single-pole single-throw solid-state switch. With a zero signal applied to the base of the transistor, it turns off, acting like an open switch, and zero collector current flows. With a positive signal applied to the base of the transistor, it turns on, acting like a closed switch, and maximum circuit current flows through the device. The simplest way to switch moderate to high amounts of power is to use the transistor with an open collector output, and the transistor's emitter terminal connected directly to ground. When used in this way, the transistor's open collector output can thus sink an externally supplied voltage to ground, thereby controlling any connected load. With inductive loads such as relays or solenoids, a flywheel diode is placed across the load to dissipate the back EMF generated by the inductive load when the transistor switches off, and so protect the transistor from damage. An ideal transistor switch would have infinite circuit resistance between the collector and emitter when turned fully off, resulting in zero current flowing through it, and zero resistance between the collector and emitter when turned fully on, resulting in maximum current flow. Even though the transistor is not a perfect switch, in both the cutoff and saturation regions, the power dissipated by the transistor is at its minimum. PNP Transistor Switch. We can also use the PNP transistors as a switch. The difference this time is that the load is connected to ground, and the PNP transistor switches the power to it. To turn the PNP transistor operating as a switch on, the base terminal is connected to ground or 0 volts as shown. Darlington Transistor Switch. Sometimes the DC current gain of the bipolar transistor is too low to directly switch the load current or voltage, so multiple switching transistors are used. Here, one small input transistor is used to switch on or off a much larger current handling output transistor. To maximize the signal gain, the two transistors are connected in a complementary gain compounding configuration, or what is more commonly called a Darlington configuration, where the amplification factor is the product of the two individual transistors. The overall current gain beta, or HFA value of a Darlington device, is the product of the two individual gains of the transistors and is given as a side. So Darlington transistors with very high beta values and high collector currents are possible compared to a single transistor switch. As well as its high increased current and voltage switching capabilities, another advantage of a Darlington transistor switch is in its high switching speeds, making them ideal for use in inverter circuits, lighting circuits, and DC motor or stepper motor control applications. One difference to consider when using Darlington transistors over the conventional single bipolar types, when using the transistor as a switch, is that the base emitter input voltage needs to be higher at approximately 1.4 volt for silicon devices, due to the series connection of the two PN junctions.